Hello again everyone, welcome back to ptet.chemistry channel. So this is Mr. On and this is the third of 10 video in this series of infographics provided by the Cambridge Assessment International Education. So I don't make these infographics, please don't credit me. So this infographic will be available as a Google Drive file via a link in the video description, so you can use them as you wish in your classroom or share with your friends or whatever. But bear in mind that this is not a syllabus specification. This is basically how the topic on controlling reactions can be interrelated, so that you can understand about making sense of what you're learning as to what might come next, or trying to relate to what you have learned in the last couple of weeks or last couple of months or throughout the whole A-level course. All right, so a lot of chemistry students, in fact all chemistry students, will be expected to know about the idea of enthalpy change by now. So exothermic reaction release heat energy to the surrounding, endothermic reaction takes in energy from the surrounding. So a lot of students will have been confused with this idea of system versus surroundings. If you are still very confused about it, I suggest you read out on what is the system, which is basically the reaction itself, okay? Whereas the surroundings are everything around it, and that includes the water that makes up a lot of solution, or it could be the whatever solvent you are in, or the air around you. So those are the surroundings. And of course that relate to this kind of enthalpy, energy profile diagrams, where you need to take into account the enthalpy change is from the reactant to the product. So here is an exothermic reaction because it's going down. The reactant have lost energy. It's lost energy to the surrounding. So your product have lesser energy. And activation energy is the energy required to go from the starting point to the top of the hump. All right. So these are all basic definitions. And obviously chemical reactions involve bond making and bond breaking. So back in O-level GCSE, you have done something simple that relates making bond to akin to releasing energy, and that's what you classify as exothermic reactions, and vice versa for endothermic reactions. So it's the overall change that result from whatever energy that get released when you make bonds, and the energy change when you break bonds. So it's the balance between the two that will govern the whole reaction, whether it's exothermic or endothermic. All right, and then one thing that a lot of students didn't realize is that these are covalent bonds between the carbon and the halogens. So they have bond length, because obviously as you go down the group 17, the bond length gets longer, okay, and therefore the bond energy gets weaker. All right, so the bond energy gets stronger that way, but it gets weaker that way, okay. You need to think about what is the definition of covalent bond in terms of how strong the bonding electrons in between are attracted to the nucleus of the two atoms as they get further and further apart due to the bigger halogen atom. So these are all in group 17 as well. And then electronegativity affects the bond polarity, which can affect how the bond will react. Okay, so there's the bond energy and bond polarity. Those two can affect how this type of bond will react, especially in the context of halogenoalkane under organic chemistry. In terms of enthalpy of combustion, we talk about the release of energy. Okay, because enthalpy of combustion is always exothermic. That's how we get energy to run our cars as fuels, to run our engines and aeroplanes, etc., etc. in industry as well. And of course, like how things like catalysis can help to make the reactions a lot faster by providing you alternative reaction pathway with a new low activation energy. So a lot of these dirty pollutants that come from your car engines, oxide of nitrogen, carbon monoxide, or unburned hydrocarbon, they form much cleaner products as they come out of the car engine after they pass through the catalytic converter. And then there's also that idea about using Hess law, which is quite new in A-level chemistry. And basically it says that as long as you start from the same point and has the same end point, start from the same point, ending at the same point, it doesn't matter which route you take, whether it's direct or whether it's indirect. Okay, so here you will have done quite a lot of calculation examples involving enthalpy of formation and enthalpy of combustion. So it's really confusing sometimes, like which one to use. You should be asking yourself really, what is the reaction that you are trying to find? and from there you should be thinking what data are you given. All right, so I've covered in my topical playlist examples of these kind of calculations involving formation and combustion, so you can watch how I explain them in detail in those topical playlists. Okay, so as we burn these fuels, we can either absorb energy or we can release heat energy, so it can be exo or endo that accompany the reactions. But along with it, we can get some other side product which could be environmental pollutants, and that is where you could get pollutants containing sulfur if you burn fuel that contains sulfur, or you could come from natural resources like natural phenomenon like when you have lightning. That's enough. Not lightning, volcanic eruptions for the release of sulfur dioxide. Lightning will give you the oxides of nitrogen because lightning has enough bulk of electricity that can break the nitrogen triple bond. Anyway, so those come under environmental chemistry. It's quite a big component of AS level chemistry under inorganic chemistry as part of nitrogen and sulfur case study. Of course, you could relate enthalpy change with redox as well. So associated with a redox reaction where you have oxidation or reduction, then there's associated energy or enthalpy change associated with it. Although these are typically covered in an A2 component where we talk about relating standard cell potential. That's to take into account the standard reduction potential that happens in a half equation and accounting for whether reaction is feasible or not in the forward sense. And then there's obviously catalysis, as I mentioned just now. So this is the Maxwell-Boltzmann distribution diagram. Gotta know the axis refer to the amount of molecules or proportion of molecules with energy E, and the x-axis is just energy. The area under the graph represents the total number of molecules. So when you have a catalyst, you increase the area under the graph because you have a new lower activation energy here, whereas this is the all higher activation energy. So now by having the new lower activation energy here, lower energy, you will have increased the area under the graph. They will have enough energy to react because the energy has to be greater than or equal to the activation energy for them to react, right? So Maxwell-Boltzmann distribution diagram tells you the proportion of molecules having enough energy to react, and that's what tells you whether you have more or less effective collisions. Very important when you take into account the effect of temperature on the rate of reaction at A-level chemistry. Typically in GCSE or O-level, you have just done collision frequency, which is related to just how frequently they collide, whereas here we are dealing with how much proportion of the reacting molecules have enough energy to react. So these two factors are not related to each other. In fact, both of them contribute to rate of reaction, as you have done under rate of reaction. If you do a certain specification, you will have rate is equal to AE to the power minus EA over RT, and you could take the log of it. In fact, I think in CIE, they love to give this as a paper 5 or even a paper 3 question. So you will get y is equal to a constant, and there is your x-axis, and there is your gradient. And by plotting a graph of log 1 over time, because you don't really measure rate, you measure the time, which is inversely proportional to rate, and you can put these equations, set up a table, and plot a straight line graph where you can get information on this EA over R, and you can find the EA for the reaction, activation energy for the reaction. So this equation is called the Arrhenius equation. You don't necessarily have done it in your Cambridge International A-level, but it's quite a popular equation in other examination board. And what's important really is this part of the equation actually comes from the Maxwell-Boltzmann distribution, and A is actually the collision frequency. That's what I meant by two things. They are not the same, but both of them contribute to the rate equation and therefore how fast your reaction is going. All right. So you have known that rate depends on a lot of factors, depending on concentration, depending on surface area, depending on whether you use a catalyst or not, as well as dependent on temperature. That's very important. So all these are explained under the rate of reactions topical playlist on my channel if you navigate around. So definitions of homogeneous and heterogeneous catalysis. So these are covered in AS, but obviously they are more frequently asked in A2. That's not to say that they can't be asked in AS chemistry at all. Yeah. So you should have known examples of homogeneous and heterogeneous examples. You should be able to write an enzyme catalysis essay as well at the A2 level. Which typically is worth between 2 and 4 marks if you draw the lock and key mechanism. You talk about active sites. You talk about the lock and key substrate, and you talk about the products, and the enzyme remain unchanged because your catalyst, in this case your biological catalyst, will be unchanged at the end of a reaction. All right. And then they relate enthalpy change, chemical energetics essentially, to equilibrium reaction. So what is meant by dynamic equilibrium? So a lot of students know only one part of the definition, that's to do with rate. However, they forgot that it's also to do with the concentration of the products and the reactants that remain unchanged when you reach dynamic equilibrium. There's actually something wrong with this equation they've given here. This shouldn't have been multiplication because, as you know, the number in front of the balance equation goes out as a power, and then you divide by the product of the concentration of the reactants raised to the power, right? So it should have been multiplied and not a plus. But when you're doing KP, you're dealing with partial pressure. So you're dealing with partial pressure, and therefore it is also not a plus. It also should have been a multiply. I don't know what they have done there, okay? So I do not produce these infographics, and I think like students who have been well aware that it wouldn't have been a plus, it would have been the multiplication, yeah? But I can tell you one thing, partial pressure is not the same as concentration. So you need to be aware, especially students, you should be aware that they are not the same. Calculation involving KP involve like 1 or 2 more steps. You can watch my topical playlist on calculating equilibrium constant that involve Kc and Kp if you're unfamiliar with it. Very important to keep track of what has reacted and what has formed, all right? There's a lot of things that are in equilibria or reversible reactions, and they relate to ionic equilibrium. And ionic equilibrium, there's talk about acid and bases. When the acid donates the proton, it becomes something called conjugate base. When the base accepts a proton, it becomes something called conjugate acid. Strong acid and weak acid, or strong base and weak base, they obviously relate to A2 chemistry, where we talk about calculating pH. What else? We talk about solubility product. We talk about partition coefficient. We talk about many other things, all right? So a lot of equilibria are revisited in a more complicated setting at the A2 level, but at AS level, you have done all of this anyway. So this is it in this video. So like I said, these are not content-based video. These are not specification or going through the syllabus kind of video. It's just basically showing you how chemists control the reactions based on this infographic provided by Cambridge International, all right? So I hope that was useful, and I don't think it's necessarily useful. It's more for you to see how the topics are interconnected together, okay? So this is the third of 10 video series. I'll see you in the next video, and thank you for watching. Do subscribe to the channel and share this video if you find them useful, and I'll add a couple more MCQ tutorial in the next few days, all right?